volume change. But before we begin, I'd like to go over some of the housekeeping for today. Anyone who is collecting MCEs will be able to scan at the end of the session via QR code that will be displayed on the screen, or there will also be one printed on the door that you can sign in there. And so it'll all be done through the FeedLoop app. You can go to find the session you wish to check in by clicking on the check-in icon and scan the QR code. If you wish to keep track of the sessions you attended manually, you may request an MC tracking sheet at the help desk. It is now my pleasure to welcome Andre Raffla from the University of Ottawa to present Trans-Tibial Prosthesis 3D printed insert to accommodate residual limb volume change.
Hello everyone, thank you Amy for the introduction. As she said, my name is Andre Raffla. I am a master's student at the University of Ottawa. I'm working under the co-supervision of Professor Edward Lemaire and Professor Nathalie Badour. I'm here to present to you our new solution to accommodate for a long-term residual limb volume change, particularly for transtibial prostheses. To start off, I have no conflict of interest to disclose. This project was funded by the NSERC Discovery Program and by the Create Ready program. As you all may know, creating and owning a prosthesis can be very expensive, and it can get very expensive very quickly. Many amputees go through 3 to 5 socket changes within the first year post-amputation because the residual limb starts healing and shrinking. On top of that, an average transtibial prosthesis in Canada costs over $4,000, and you can see how it can get very expensive very quickly. Our goal in this project was to resolve this issue without compromising on the quality of care, while creating an inexpensive and cost-effective solution to try to alleviate some of that financial burden on both the amputee and the healthcare system that sometimes subsidizes these sockets. We also wanted to create a quick solution to alleviate, as I said, like some of the time restraints on prosthetists and amputees, the wait times to get their sockets. And we wanted to create an automated or a semi-automated process so that's easy for prosthetists to pick up and go without having to learn many new complex techniques to create the insert, which is what we're calling the device that we created. And finally, we wanted to create either a product or a workflow that's ready to use as soon as possible to help as many people have them benefit from the device as quickly as possible. It might not be the most streamlined process, but we wanted something that works right away without compromising on their care. So the solution that we came up with was when the prosthesis decides that an amputee needs a refitting, they would ask the amputee to come into the hospital or to the clinic, have their residual limb scanned, and then we would combine this scan or the rectified version of the scan with the old rectified scan that was taken to create the initial socket. We would then combine the two scans, align the two models together, create a model of the thickness in between these two models, which is what we're calling the insert. We would then 3D print the insert and have it integrated into their existing sockets, removing the need to get a new socket completely during that initial stage where they're going through many sockets until they can finally stabilize. It's important here to note that this is an insert. It's not a liner. Inserts are likely to be used in conjunction with liners. The insert is simply reconstructing the inside shell or the inside surface of a socket. Going through the literature, there were 2 main papers that we would like to discuss or that we need to share. One of them was by Sanders and co., which mentioned such a process as a possible future possibility. But more recently and more importantly, there was a paper by Nickel and co., where they ran a proof of concept study on a very similar process. What they did was they recruited a participant, a transtibial amputee, with already a good fitting socket. After then they'd taken a scan of their limb, had it rectified, and then they expanded it outwards, globally, uniformly outwards. And then they took this globally enlarged scan and created a socket that is oversized. This oversized socket would be the loose-fitting socket in this case. And they ran a comparative study between the loose-fitting socket, the well-fitting socket, and the loose-fitting socket with the insert integrated inside. The participants reported back a lot of positive feedback. You can see here that they had a socket comfort score of over 8, and they had many positive comments such as, I feel level, I think it's just as good as my existing socket, and I couldn't feel a heat difference in the short walk that they took. The last point here is significant because obviously they're using a much larger socket than they would normally need to. This is a concern that we would like to keep monitoring in the future to see how it's affecting amputees and patients. Furthermore, more on the quantitative side, you can see that there was a significant benefit to using the insert, where we had a 6% improvement in the walking distance or how comfortable they were walking with the insert socket system. Compared to the already existing good fitting socket, we had an insignificant less than 1% reduction in the walking distance compared between the well-fitted socket and the socket insert. One of the drawbacks of the previous system was that they expanded the scan of the limb universally and uniformly outwards. This is not the real world experience, as we know that residual limbs usually reduce in size in non-bony areas much more than in bony areas. And that's why we needed to have two different shapes, one on the inside of the insert and one on the outside of the insert. So for our solution, we decided to go with an open source software, 3D Slicer. We wanted an open source software so that it's easy to implement worldwide, and for future streamlining of the process, it's just easy to edit and change little parts of the process. 3D Slicer is a well-recognized software. It's currently mostly used for dental applications and for diagnostic imaging. Nevertheless, it's recommended by many authors and was shown to have good clinical experience when compared to other commercial products that had similar features. On top of 3D Slicer, we're also using a plugin called CMFreg, which does a PCA, principal component analysis, to align the two shapes to get this automatic first alignment to help the prosthetist. It usually aligns between two segments, but thankfully Slicer simply just converts models into segments and back into models when needed. Some of the other features of Slicer 3D that we found were useful was the ability to manually control the position of each scan, which is important because after we get that initial automatic alignment, we needed to give the prosthetist full control over the position of the inside scan compared to the outside scan so that they make sure that the shape is looking right and that the user will be able to stand upright. There's no issues. If there's any issues with the rotation, the prosthetist can easily fix those. Other than the manual position controls, there was also the option to fill a solid and do Boolean logic operations, which is important because after we get the alignment, what we do is convert it into a solid model. Then we would fill in these solid models to create one block of each scan. And then we would subtract the bigger block from the smaller block, creating the thickness, which is the insert. Once we had the insert prepared, we then used post-processing features such as smoothing and trimming to create the final shape of that insert that is good to use for the user. Once we had the shape ready, we moved on to 3D printing. And you can see here, after talking to a prosthetist, we asked them what they think that insert thickness will have like a range of thickness. They told us that it's gonna be between 3 millimeters and 7 millimeters. You can see here, this is like an example of a 3 millimeter, and this is the 7 millimeter thick cubes. And we made small rectangular cubes with different materials, with different printing patterns, and with different infill percentages, just to try them out. And we tried them out in compression with these 3 forces you can see right there. More on these forces and where they came from in the next slide. We tested 2 materials mainly, Ninja Tech Cheetah TPU, which is a TPU with a shore hardness of 95A, and we also tested nylon. We needed a flexible material so that it's easy to integrate into the socket once the insert and the socket are ready. We found that TPU is a little bit more flexible and it produced good results, so we went ahead and used TPU. For the print pattern, we went to the cubic pattern because we wanted to give the insert a little bit of more isotropic properties to be able to withstand the forces from different directions, as would be experienced in the socket insert as used by the user. And finally, we went with a 35% infill, which was the lowest we went comfortably. while still giving it as light of a weight possible and still maintaining the strength needed. Cubes printed with these printing parameters were able to withstand testing in compression. The way that testing worked was we would load it at each load, and then we would try to maintain that load for 30 seconds, and then let the block rest for 15 minutes before moving on to the next load, and so on. What we've seen that the blocks were able to maintain their elasticity. There wasn't any visible damage, and the test was repeatable, which means that they did not lose, again, any elasticity. The compression at the proof static load, which is the 2000 Newton load, was less than 10%, and the compression under the ultimate load, which is the 4000 Newton load, was under 15%. Once we had the printing parameters chosen, we went ahead and 3D printed the insert, and for the mechanical testing, while we were creating the protocol, we didn't really know how to test the insert on its own because this is a completely new device. There's no protocol or any research into how we would like them to function. So we went ahead and integrated it into a socket and tested the insert socket as just a regular socket. We used other published articles and the ISO protocol for lower limb prostheses. As documented, the insert had to go under the static and cyclic loads. The static cyclic loads in here are the 3 loads you saw on the previous slide, which is why we chose them to test the blocks, which is the 1000 and 2000 and 4000 loads. These are called the initial, proof, and ultimate static loads. We would then load the socket. You can see here on the right, this is the toe configuration over here. And then it's the forces being applied using a ball, which is a point force. And then for the heel configuration, it was completely different, where again, we're applying a force on the back end of that base plate. We would then apply the load, again, get it up to the required force, let it creep for 15 seconds, and then letting it rest. Let it creep for 30 seconds, and then letting it rest for 15 minutes before moving on to the next load. For the cyclic testing, we tested only the toe configuration, since we know that sockets usually only fail in the toe configuration. So we didn't really need to test the heel configuration as mentioned by other published authors. And it was done for 1 million cycles, since in 2 million steps, there's 1 million steps on the toe configuration. We did it at 1.5 hertz, and here are the results. So at the top here, you can see the results for static testing. Here's in the heel configuration, here's in the toe configuration. And you can see here that the graphs are overlapping almost perfectly, which is an indication that the insert never lost its elastic properties and was able to withstand the loading. There's no sudden jumps or skips in the material, which also means that the material did not collapse on itself. We also checked visibly to see if there's any signs of failure, and there was no visible signs of failure. On the bottom here, you can see the cyclic testing. We measured 2 main parameters, which is the loading and the displacement. For the loading, that's what we were trying to maintain. We were trying to maintain a load range of 15 newtons to 1,330 newtons, which is a range of 1,280 newtons. And we were monitoring the stroke. You can see here that the stroke was almost steady the entire time. These small jumps here are because testing was done over a couple of days and I had to go in and fine tune, but as you can see, the system was able to slowly stabilize again. So what did our project show? So far, our project has shown that FDM printing is a viable solution to creating inserts. This is important because it's accessible in all clinics and it's cost effective. The insert was able to withstand static and cyclic testing. And we also shown that open source software was a viable tool to create the initial automatic alignment. Finally, it's important to note that we needed to use 3D scanning and CAD software to be able to create the final shape. So this is moving forward a limitation that we need to consider. And with improvements in technology, we'll be able to create better scans and better shapes. Currently, now that we've done mechanical testing, we've moved on to create a pilot clinical trial. We've already spoken with 3 different participants, and we're working with them to create their insets to get some patient feedback. Moving on, we would like to create some improvements to the workflow, maybe create the improvement in the alignment algorithm. Right now we're using PCA alignment, which is the most commonly used alignment, but research has shown that different alignment algorithms can have different benefits depending on the application. We would also like to test different 3D printing parameters to see their effect on the inserts. Thank you everyone for listening, and I have 20 seconds for the questions.
We have 1 minute for questions.
Yeah.
Any questions?
Are you able to scan the inside of an existing socket?
No, so what we're doing is that we're taking the existing scan from the outside for now. Is another question? Yeah.
Hi, really interesting presentation, thank you. I was curious, so this is meant to be used in conjunction with a liner, which is what you said?
Yeah.
So how does it get on? So like it'll be like in the socket, then the liner?
So the idea is that we will press fit the insert into the socket, and there's like a small attachment at the bottom that they use already for sockets, and it would basically fix everything in place, and then they would use it as a regular socket after that.
Right, so I guess like if this is meant to be kind of filling in any like minor like deviations in volume, like would there be concerns that if there's like minor fluctuations like day to day, like it would be like even tighter, do you think?
So for the day-to-day fluctuations, we're expecting the insert to perform very similar to what current sockets perform, so what they're doing right now. Ideally, we would take a couple of scans to know like what's the biggest volume, so that for day-to-day fluctuations, it doesn't cause an issue in compression and all that. Yeah.
Unfortunately, that's-
Friction? Sorry.
Unfortunately, that's all the time we have for
Feel free to reach out to me
this
on my email.
afternoon.
I'll answer any question.
Yeah,
there.
please
Thank you
do
so much.
find Andre later this afternoon, and we'll be getting started with our next one.